Hi everyone, my name is Wischnewski. I'm from the Donders University in Nijmegen in the Netherlands. And in the last 3 years we've done two exciting experiments in the lab which you see behind me. And today I want to talk about that in this little presentation. So yeah, let's get started. So in the study we tried to influence reversal learning performance by using transcranial alternating current stimulation. And I presume that most of you are familiar with tACS, but just to quickly reiterate, with tACS we use an electrical stimulator to induce some oscillations on the scalp, which then are thought to entrain oscillations within the brain. So for example, if you apply oscillations on the scalp in a theta range, then you would expect that theta oscillations within the brain are enhanced. And the same is true for any other stimulation frequency, for example, the beta frequency. So in this study, we wanted to use those the tACS to have an effect on reversal learning. So people in our study received a task in which they saw two numbers, as you can see in the left upper corner. And those two numbers represented points that they could either win or lose. So when they choose the 25 option, they could either win 25 points or lose 25 points. Or when they choose the 5, they could either win 5 points or lose 5 points. So basically those reflect a high risk and a low risk option, because with the higher number you can win a lot, but you can also lose a lot. And with the lower number you can win just a little bit, but also lose just a little bit. And our task, as you see in the left lower part of the screen, you see that we designed the task in such a way that in the beginning the high risk option was the better option in 80% of times, and only in 20% of times the low risk option would be better. And over time people should learn this, and then after a while this switches to the lower option being the better option, and then after a while it switches back to the high risk option being the better option. And designing the task in such a way allows for looking at learning in two different ways. So first you can look at the learning speed, which is basically the number of trials needed for people to reverse their strategy from a high risk strategy to a low risk strategy and back. And second, the rule implementation, which basically is how well they implement the rules. So if the high risk option is the better option, are they actually taking the high risk? And if the low risk option is the better option, are they actually taking the low risk? Or are they hovering somewhere in between and not really know what they're doing? So we wanted to look at those two aspects of learning. And also we wanted to have an idea what happens to the brain when we stimulate with tACS. And that's why we also recorded a resting state EEG before and after the task. Ideally you would want to do this during the experiment, but looking at EEG while applying tACS is very, very difficult to say the least, and we were not able to do that, so that's why we didn't. So what did we do? We applied theta. In the first experiment, we applied theta oscillations, because we know that theta oscillations are important for reward driver motivation. So when there is a learning task like this, where there's points involved, you would expect that theta oscillations are important for that. We know that theta oscillations are reflected by long-range cortical to subcortical interactions, and also interactions between the left and right hemisphere, and that's why we stimulated left and right frontal cortex. We used 1 milliampere and stimulated during the entire task, which was around 12 minutes. So what did we find? So we tested a total of 50 participants, which is 25 per group, because we had one active group and one sham group in which people didn't receive any stimulation. So the dots represent basically the average risk-taking participants took. And as you can see, over time in the first 20 trials, people learned that the high-risk option is the better option. And then from trial 40 onwards, you see that people tend to go to the low-risk option, and that's correct, because that's when it reverses to the lower risk option. And the lines represent basically how fast people do this. So what you can see is that there is a small but significant difference in how fast people learn the switch from high risk to low risk. The people who received the real tACS, they needed less trials to reverse from high risk to low risk compared to the people who received the sham stimulation. In the second reversal from low risk to high risk, we see the same trend, with people who receiving the real tACS being a little bit faster. However, this was not significant. So you would say, okay, this is cool. tACS is good for reversal learning performance. However, when we look at the very last block, we see that people who received the real tACS, they didn't use as much high risk as the people who received the sham stimulation. And that is interesting because in the last block, you should take the high risk. That means basically that the rule implementation, basically the rule to use a lot of high risk, wasn't that well implemented at the end by the people who received real stimulation. So although tACS is better for or improves learning speed, it's not necessarily good for the rule implementation. So what happened when we look at the EEG results? We first looked at coherence measurements between left and right hemisphere, but we didn't find anything. I don't even have a graph of it because it's just very, very sad to see almost. So that's why we looked at the power. And what you see here in this graph is the change from pre to post difference between the real and the sham tACS. And what you may expect is that tACS increases theta power in the frontal cortex. This didn't seem to be the case. If anything, there was the opposite. If you look at the white bar in the left hemisphere, there was, if anything, a decrease in theta power. However, it was not significant, so we should conclude that there was no difference. Also, there was no difference in the right hemisphere. However, my supervisor suggested me to look at the theta-beta ratio, and that is because in research with ADHD patients, the theta-beta ratio is often used as a measure to look at cognitive control and cognitive performance. And what we see in patients with ADHD is that they tend to have higher theta-beta ratios, so more theta oscillations compared to beta oscillations, and this does reflect poorer performance in reversal learning tasks, where they often persevere and stay with their first strategy and never really implement the new rule. So analogously, you would expect that a lower theta-beta ratio would be associated with better reversal learning performance, and that was the case here. Here we saw that the theta-beta ratio, at least in the left hemisphere, was decreased from pre to post in the real tACS conditions. So, of course, these resting state measurements were done after the task ended and after stimulation ended, so whether this really reflects what happened during the task is a little bit hard to say, but at least it does seem to make sense. It does seem to make sense that a lower theta-beta ratio is coupled to better reversal learning performance. All right, so after that we thought, okay, theta-beta ratio, that's interesting, but there is a beta in theta-beta, so also we should have a look at the beta oscillations. So we thought, why not do the exactly same experiment, but this time with beta oscillations? We tried to replicate the study completely. However, we used a slightly different montage in which we used an in-phase and an out-of-phase montage, basically to have one hemisphere in the same phase or in the opposite phase. However, I should say that since we didn't really focus on two separate areas, I'm not so sure that that this really made sense afterwards. At the time, it seemed like a good idea, but afterwards, I'm not so sure that this was the best way to look at it. In the results, you will also see that that there's no real difference between the two conditions. So yeah, I'm not going to go into too much detail about that. Now, of course, if you have any questions, you can ask me afterwards. Another thing is that we used some LED lights next to the eyes, which were flickering, to control for phosphines, which people often observe during beta stimulation. And we also used those during the sham stimulation, so that the flickering of the lights would be the same between the sham and the real active conditions. So what we found in the three conditions is that reversal learning speed wasn't different between any of the conditions. So active tACS, whether it was the in-phase or the out-of-phase one, wasn't faster or didn't produce faster reversal learning than in the sham condition. However, what we did see is that people who received active tACS implemented the rule better, particularly the rule of taking low risk in the low risk block. And also what you can see is that there's no real big difference between the two tACS conditions. And as I said, I'm not so sure that it was so necessary to have those two conditions. We probably could have just used the same montage as in the first experiment, but yeah, that was just an idea I had back then. So in this case, we find no improvement on reversal learning speed, but we do find improvements on rule implementation. So how did the EEG look like? So in the EEG, we find that from pre to post, the theta-beta ratio went up in the sham condition. However, this was not the case for the active tACS conditions. So basically what you could say is that in the active tACS conditions, theta-beta ratio was lower after the task compared to sham. However, again, this is a measurement after the task, not during the task, so whether this is a good representation of what happened during the task is a little bit hard to say. But again, it seemed that better reversal learning performance was associated with decreased theta-beta ratio, which at least makes sense. So what can we conclude? Well, we can conclude that theta tACS improves reversal learning speed, but doesn't really help with rule implementation, whereas for beta tACS, the opposite was found. Reversal learning speed wasn't affected, but rule implementation seemed to be better. So this suggests that those two oscillations have two different functions in learning, in reversal learning in the frontal cortex. However, interestingly, in both cases, the theta-beta ratio went down, which it's very interesting. It does make sense if you look at the analogy of the ADHD patients, but it is quite interesting to figure out in future research how this theta-beta ratio is actually related to reversal learning, and particularly those two different aspects of learning. So yeah, that is it. I hope you enjoyed the talk. If you have any questions, please let me know. And of course, you can always send me an email or ask me in the discussion afterwards. And I hope you enjoyed it. I think this is a cool research that prompts some interesting future research. And yeah, with that, I hope you enjoy the rest of the conference. Thank you.